Hello, I'm Norman Wildberger. In this lecture, we're going to look at cubic splines. We're going to look at how we use cubic polynomials to create little arcs to create a smooth curve through a given number of points in the xy plane. This is an interpolation problem. So in our last video, we had a look at the cubic de Castelnau-Bézier curves, which were a way of describing curves that are very important for design work, where we have a number of control points, and if we vary these control points, then we can vary the corresponding curve. And so the idea was that if we had a curve, then we could cut it up into little pieces and use a number of these de Castelnau-Bézier curves to smoothly recapture that curve. All right, today we're going to go in a slightly different direction, but very closely related. We're going to apply cubic splines to the interpolation problem. So with this interpolation problem, we have the xy plane as usual, and a finite number of points. And our aim is to try to find a curve that smoothly passes through those points. And of course, that may not be unique. There might be lots of curves that do the job. One way of doing this that we already know is to find a single polynomial that goes through the number of points. So if we have 2 points, for example, then we can find a linear polynomial that goes through them. If we have 3 points, then we can generally find a quadratic that goes through them. 4 points, we can fit a cubic. 5 points, we can fit a quartic, and so on. As the number of points increases, the dimension or the degree of the polynomial that we need to use goes up. So today we're going to look at a different aspect of that problem, where we're going to attempt to find a curve made up of just a bunch of cubic arcs. So we don't want to go past degree 3. Degree 3 is quite nice. So the idea is we're going to create an arc between these 2 points, and then another arc between these two, another arc between these two, and another arc between these two. And we're going to create these arcs so that they're smoothly joining at the points where they meet, giving the impression that it's all really one curve, while really it's a number of curves joined together. Really the same kind of thing that we're doing with the de Castelnau-Bézier business for design purposes. All right, so to be specific today, we're going to look at these 5 points. So the point 0, 1, point 1, 3, 2, 2, 3, 2, and 4, 1. And the question is, how do we find cubic arcs that are joining these points smoothly? So from a linear algebra point of view, we're working in the space P3, which is our familiar space of polynomials of degree 3 or less, which I'm hoping is slowly becoming your favorite mathematical space. We've seen it quite a lot, and we're going to look at it some more today. So the typical element in this space is something like this. That's a polynomial of degree 3. And I like to have my variable b alpha. All right, so this is a plus b alpha plus c alpha squared plus d alpha cubed. And we can see once again that this is actually a 4-dimensional space, because we can choose the coefficients a, b, c, and d independently, and there's 4 real choices there. Okay, so let's just have a look at the problem one segment at a time. So let's just look at the first segment. The point 0, 1 is our first point, and the point 1, 3 is the second one. So let's just consider, what do we need to do to create a cubic curve that goes from this point to this point. All right, well, let's take this particular polynomial and let's ask, well, what does it mean for p to pass through a and b? Well, if it passes through a, what does it mean? It means that if you evaluate it at 0, you get 1. So it means if we plug alpha equals 0 in here, then a has to equal 1. That's the condition for it to pass through that point. The condition to pass through the point 1, 3 is a little bit more complicated, but not much. If we replace alpha with 1, then we should get 3. So if we replace alpha with 1, then this becomes a plus b plus c plus d, and we want that to be equal to 3. So those are the two conditions necessary for a general polynomial like this to pass through those 2 points. And there's only those two conditions, and we started with 4 degrees of freedom. So there's really a 2-parameter family of such cubics. We have some freedom in choosing cubics that pass through these 2 points. Maybe this is one of them, maybe this one is another one, and there's quite a lot of them. There's a 2-dimensional family of such cubics. So to specify any one of them, what we could do is we could specify tangent directions at A or B. In other words, to pin down the possibilities, we could say, well, we want a polynomial which happens to be tangent to this line at the point 1, or maybe tangent to this line, or maybe tangent to this line. That's essentially specifying a first derivative at A. Or we could also be a little bit more sophisticated and say, well, in addition, we want the second derivative, that's a calculus notion, to have a certain value at A. Or maybe we could require that the tangent at B be a certain amount, or that the second derivative at B be a certain amount. We have some freedom about what conditions we want to impose on this curve. Basically, we can have 2 extra conditions because we have 2 degrees of freedom. Okay, so it sounds like we're going to need a little bit of calculus for this lecture. In fact, if you haven't taken calculus, don't worry. We really are not going to be needing calculus really at all to understand what's going on here. Right? So the calculus ideas that we do need, we can derive them ourselves just by a bit of linear algebra thinking. Okay, so what we're going to do now is we're going to relate 2 different views of this arbitrary polynomial. A view that's sort of based at 0 and another view that's based at 1, because these are the endpoints of the segment that we're considering. So what we're going to do is we're going to consider what are called Taylor expansions, and I'm going to show you what I mean by those. So let's start with a general polynomial in our space P3. So here it is again, a plus b alpha plus c alpha squared plus d alpha cubed. And I'm using alpha here instead of the more familiar x, but it's pretty well the same thing. Now I'm going to make a little calculation, which is very simple, or pretty simple, but very instructive and important. And what we're going to do is we're going to translate this polynomial by 1. So we're going to look at p of alpha plus 1. In other words, we're going to replace these alphas here with alpha plus 1s. So here's the alpha plus 1, and alpha plus 1 squared I've written out using the binomial theorem. And alpha plus 1 cubed, I've written that out too. Alpha cubed plus 3 alpha squared plus 3 alpha plus 1. And now let's take that and expand it out and collect terms. So the constant term will be a plus b plus c plus d. And then the linear term in alpha will be b plus 2c plus 3d. And the quadratic term in alpha, the alpha squared term, will have coefficient, well, there's a c from there and a 3d from there. And the only thing left over is the alpha cubed term, which will have a coefficient of d. Now I'm going to rewrite this. I'm going to rewrite this by replacing alpha with alpha minus 1. I'm going to undo what I seem to have just done. So if we just take this expression and replace alpha with alpha minus 1, then this becomes just alpha. So we just get p of alpha, which is just p. And here, this alpha is replaced with alpha minus 1, this one with alpha minus 1, all squared there, and this alpha with alpha minus 1, and it gets cubed. So we've translated it by 1 first, rewritten it, and then translated back, so we still have the same polynomial that we started with, but now it's written in a rather different way. So we've started with a polynomial in powers of alpha, and we've managed to rewrite it using just a bit of high school algebra, that's all. We've managed to rewrite it in terms of powers of alpha minus 1. This is called the Taylor expansion of this polynomial around alpha equals 1 because, all right, we've got terms alpha minus 1. So this is what's called a Taylor expansion in calculus. And for those of you who have studied calculus, you will know that inside here there are various derivatives of the polynomial. That this thing here is essentially the derivative of this polynomial evaluated at 1. This is essentially the second derivative. Actually, it's a second derivative divided by 2 evaluated at 1. And this is essentially the third derivative divided by 3 factorial, which is 6, evaluated at 1. But notice that I've managed to get these coefficients without any differentiation. So there's been no limits, there are no real numbers, there's none of that, all that calculus framework required. We're just translating the polynomial once and then making another substitution and having a look at what we get. Okay. So this is a very simple approach and a very powerful approach to differential calculus. And in my Math Foundation series, I'm going to show you that this is actually a very viable algebraic alternative. It forms the foundation for a much more algebraic point of view towards calculus. So in other words, calculus becomes a little bit more subservient to linear algebra rather than the other way around. Okay, but anyway, so now we've got this Taylor expansion of the polynomial around alpha equals 1. And if we wanted to, we could do this with alpha equals 2 or something else if we wanted to as well. If we have a linear algebra point of view, we like to take something like the previous slide's formulas and compress them, make them more efficient, ask, what's the essential aspect of this? And the answer is that there are really 2 vectors floating around. The vectors of coefficients of these polynomials. So we're going to call those Taylor coefficient vectors. So we're just going to rewrite the information and say that the polynomial p has this as the Taylor coefficient vector at the point 0, and it has this as the Taylor coefficient vector at the point 1. Here are just the coefficients of alpha minus 1 to various powers, and here are the various coefficients of alpha to various powers. And we'll distinguish those by putting a 0 here and a 1 here. Alright, so once we've done this and encoded the information just in terms of vectors, a natural question is, well, what's the relationship between these 2 things? Is this a linear operation to go from this vector to this vector? We can see that it's linear because the A, B, C, and D here appear just linearly. We're just taking linear combinations of them in the entries here. That means that we can actually write this as a matrix operation. And in fact we can. Here's the formula. That this P sub 1, the Taylor coefficient vector at 1, is obtained from the Taylor coefficient vector at 0 by multiplying on the right by a certain matrix. This matrix right here. So if you imagine this vector here just sitting right here, A, B, C, D, I remind you how you multiply. So if we have A, B, C, D times this matrix, the first entry will be A plus B plus C plus D, which is correct. The next entry will be 0A plus B plus 2C plus 3D, right there. The next entry, 0, 0, then C plus 3D, and the final entry, 0, 0, 0, D. It's sort of obvious, just from matrix multiplication, that this matrix equation encodes the relationship between these 2 vectors, these 2 Taylor coefficient vectors. Well, what about the other way around? That's our basic problem of linear algebra, right? How to invert a change of coordinates. We know all about that. What we need to do is we just multiply by the inverse of this matrix. The inverse of this matrix is this one right here. It looks very much like this one, except that there is a minus sign appearing on this sort of diagonal just below the main diagonal. And then there's no minus sign for the next sort of subdiagonal here. And then there's another minus sign. Now, I hope these matrices look familiar to you? I hope you say, wait a minute, I've seen those things before. Those are the Pascal matrices. Of course they are. There's the Pascal triangle sitting right here. We can't help but see it. And this is just the Pascal matrix with minus ones along alternating rows. These matrices appeared in our Walden Algebra 23 lecture, just a few lectures ago, although it's been probably more than a year since we did that. And let's give this thing a name. We called it P sub 1, so capital P sub 1, and this matrix we'll call it P sub minus 1. So these are Pascal matrices, and they are the things that encode how to go from this Taylor coefficient vector to this one, or inversely, how to go from this one to this one. So that business that we did when we had to substitute alpha is replaced with alpha plus 1, and then we made that calculation and so on. Now that we understand what's going on, we don't need to do that anymore. We just know that to go from the Taylor coefficient at 0 to the Taylor coefficient vector at 1, we just multiply by the Pascal matrix P sub 1. And to go backwards from the Taylor coefficient vector at 1 to the Taylor coefficient at 0, we multiply by P sub minus 1. This is linear algebra helping us to understand and encode very efficiently, actually a very important relation, as we'll see. This is very important, how to connect Taylor coefficient vectors at different points. All right, for those of you who have not watched Walden Algebra 23, or maybe have forgotten the main things. So that was about Stirling numbers and various bases of polynomial spaces, in particular the space P3. And the relation that we're using here is really a consequence of something very simple. Okay? It's really a consequence of just the binomial identity, expressed in this form here. So have a look at this equation here. Here's that same Pascal matrix, but now it's appearing on the left, with a vector 1 alpha alpha squared alpha cubed. So these are the powers of alpha there forming a vector. And here are the powers of, say, alpha plus 1. So this is just the binomial theorem expressed in matrix form. So for example, the third entry here is telling us that alpha plus 1 squared is, third row, 1 plus 2 alpha plus alpha squared. So that's the reason why these entries here are the binomial things, just because of the binomial theorem. Okay, a slight variant on that is this one here. Okay, what happens if we express not powers of alpha plus 1, but powers of alpha minus 1 using the binomial theorem? So for example, alpha minus 1 squared, well, we know that that's equal to 1 minus 2 alpha plus alpha squared. While alpha minus 1 cubed will be, it's actually alpha cubed minus alpha squared plus alpha minus 1 in a more familiar way. So we can see why the minus signs are appearing here. It's because we're using the binomial theorem with an alpha minus 1 instead of an alpha plus 1. And I'm also remark here that if we take this equation here and or maybe we'll just take this equation here. If we take this equation here and we replace alpha with alpha plus 1. Alright, so if we replace this alpha with alpha plus 1, then we get 1 alpha alpha squared alpha cubed here. This matrix will be just there. And then these ones will become alpha plus 1 squared, alpha plus 1 cubed. On the other hand, if we take this equation here and we replace alpha with alpha minus 1, then we get this thing as well. And then we get this matrix still. And then these ones with alpha minus 1 involved. Okay, so this makes a number of things clear. It makes it clear why these matrices are inverse matrices. Because the relationship between these two vectors and the relationship between these two vectors is an inverse one. To go from here to here, we multiply this by this matrix, and to go backwards from here to here, we multiply by the inverse matrix. So it's convincing us that, yes, these matrices are really inverse matrices. So how can we explain now that formula that we wrote down involving P0 and P1 if we didn't want to do any work initially? So the reason is this. So if you take a polynomial p, then you can think about it as being the product of the vector of coefficients at 0 with this vector, this column vector of powers of alpha. Right? Because when you multiply a row vector by a column vector, you take the product of the first entries, then the product of the second entries, product of the third entries, product of the fourth entries, and add them all up. So this is just an expression for how to write p in terms of the coefficient vector at 0. In terms of the coefficient vector at 1, it's the same story. We want to express p in terms of powers of alpha minus 1, and the coefficients there are forming that coefficient vector. It's just the product of that vector times this vector here. So now if we want to understand the relationship between the coefficient vector p sub 1 and the coefficient vector p sub 0, from this equation, suppose we just replace this vector here, according to this formula, with this thing here. So imagine just putting this thing over here where that one is. Then the two right-hand sides agree. They're both the same as this one. And then we have p sub 1 over here. And on this side we'll have p sub 0 multiplied by this Pascal matrix. So that's showing us that this relationship between these, namely this is equal to this one times the Pascal matrix p sub 1, is just an immediate consequence of these identities relating these essentially binomial powers and the expression of p in two different ways in terms of two different bases. Now there's an interesting remark that I can make here at this point in terms of this identity here has a kind of twofold interpretation that's very interesting, and in a few videos from now we're going to exploit that. So if we go back up to here and ask, what's this equation telling us? One way is to think of it or interpret it as an equation involving just ordinary vectors and numbers, where this alpha here just represents some variable number, some unknown number. Just an algebraic identity. But another interpretation is to think of this alpha as actually being a polynomial. And that what this equation is really reading is that the polynomial alpha plus 1, or maybe let's go to this one, the polynomial alpha plus 1 squared is the same as 1 times this polynomial plus 2 times this polynomial plus 1 times this polynomial. In other words, an interpretation where these things here are not so much numbers as actual polynomials. Polynomials being bigger things than just numbers. In fact, that's what's really going on here. This is a polynomial, and what we're doing here is we're expressing this polynomial as a linear combination of other polynomials. So this vector here is really a vector with polynomials inside it. Okay, we'll come back to this point. I just want to point it out for you here now. It's going to be a point of view that has some repercussions for us later. So now that we have some familiarity with this idea of Taylor coefficient vectors at a point for a polynomial, let's go back to our problem. We have these points 0, 1, 1, 3, 2, 2, 3, 2, and 4, 1, and we want to create a cubic spline joining them. And we've said that what we're going to do is do it one segment at a time. We're going to come up with 4 separate cubics that are hopefully going to smoothly fit together. So we want 4 cubics. These are elements in our space P3, which pass through the given points and join smoothly. And I've drawn them here in color. So here's one possible kind of solution. Maybe P1 looks like this, and P2, the second polynomial, like this, and P3, the third one, and P4, the fourth one. Of course, these are polynomials. These are cubic polynomials. So say P1 will extend just beyond this range. It's actually a cubic that does something like that. But we're going to ignore all of it except just the part that's in the range that we're interested in. All right, so our strategy is going to be, and this is a kind of a novel way of approaching this problem, I believe. I don't think you're going to find this in textbooks or too much on the web. So my point of view is that we want to understand this in terms of Taylor coefficient vectors, because they encode what the functions look like at the endpoints, and they allow us to smoothly make a transition from one function to another at some endpoint. Okay, so each of these polynomials, let's call them pi, and there's p1, p2, p3, and p4, has Taylor coefficient vectors at the two endpoints of its interval. So the first polynomial, which we're calling p sub 1, will have two Taylor coefficient vectors. One for the point 0, which is its leftmost endpoint, and another one for its Taylor coefficient vector at 1, which is the rightmost endpoint of its interval. Then the second polynomial, p2, will also have two coefficient vectors, one at 1 and one at 2. p3 will have two coefficient vectors, one at 2 and one at 3, and p4 will have two coefficient vectors, one at 3 and one at 4. And we want these vectors to agree up to order 2. So we want the Taylor coefficient vector of p1 at 1 and the Taylor coefficient vector of p2 at 1, in other words at the same point, to be almost the same. We want these coefficient vectors to agree up to order 2. In other words, we want them to have common first three coefficients. That will ensure that they agree up to 0th order, in other words, they'll both go through there, up to order 1, which means they'll have the same first derivative, and up to order 2, which means that they'll have essentially the same second derivative at the point where they're joining. So, in other words, this Taylor coefficient vector and this Taylor coefficient vector are almost going to be the same. The first 3 out of the 4 entries are going to be exactly the same. They'll only differ in their last entries. So that's the key. That's how we're going to generate these cubics. We're going to generate the cubics starting from left to right. And at every point, once we've picked a polynomial p1, we'll generate its Taylor coefficient vector at 1, and then the p2 one will be obtained by essentially choosing the same Taylor coefficient vector except for the last entry. The last entry will be adjusted so that the polynomial actually goes through the next control point, because p2 had better go through that point. So we've got that degree of freedom in that last coefficient to change it so that it actually goes through the point that we want it to. And then we repeat. Then we'll calculate the coefficient, Taylor coefficient of the second one at that point, and create the third one by essentially using the first 3 components to create the Taylor coefficient of it at its left endpoint. All right, so here's our example: 0.01, 0.13, 22, 32, and 41. We want to draw a cubic spline through those 5 points. We're going to start by choosing the first polynomial p1. And it's got to go through this point and through this point. And that means that we know that its first entry has to be 1. That will ensure that it goes through that point. And this plus this plus this plus this has to equal 3. That's the second condition that ensures that it goes through those 2 points. And I'm going to choose these 2 points, these 2 numbers, randomly, more or less. So I'm just going to choose the vector 1, 2, 1. And then I'm going to pick this one so that the sum of all 4 is equal to 3. So if I picked 1, 2, and 1, then I have to make that 1 minus 1 so that the total is 3. So this represents the polynomial 1 plus 2 alpha plus alpha squared minus alpha cubed. These are just the coefficients of the various powers of alpha for this polynomial. And you can check, it actually does go through the point 0, 1, and it goes through the point 1, 3. Plug 1 in here, you get 3. Okay, so we've got the polynomial, and we've got its Taylor coefficient vector at the left endpoint. How do we get its Taylor coefficient at the right endpoint, which is 1? Well, we use our basic formula, which is that the Taylor coefficient vector at 1 is equal to the Taylor coefficient at 0 multiplied by our Pascal matrix. So, we take this vector, and on the right, we multiply by that Pascal matrix. Please check that I've done it right. And we get the vector 3, 1, minus 2, minus 1. That is now the Taylor coefficient vector for the same polynomial at the point 1. And what does that mean, by the way? Well, it means that we can rewrite this polynomial in the following way. It's also equal to 3 plus 1 times alpha minus 1 minus 2 times alpha minus 1 squared minus 1 times alpha minus 1 cubed. All right, so that's good. We've picked a polynomial a little bit at random because we've just basically made up 2 of the values. We have 2 degrees of freedom, so we're just choosing some values. And now we have good control over this first polynomial P1. Now our job is to create the second polynomial. And it's got to go from this point to this point. So it's got to go through those 2 points. And we want it to match up with P1. And the way we're going to do that is we're going to choose its Taylor coefficient vector at 1 to be exactly the same as this one in the first 3 components. We're going to take the 3, the 1, the minus 2, and we're just going to copy them. That will ensure that this polynomial agrees with P1 at the point 1 to order 2. The values will agree, the first derivatives will agree, the second derivatives will agree at this point 1. And what about this fourth coefficient? Well, we have to choose that so that this polynomial goes through the point 2, 2. And that turns out to be the condition that 3 plus 1 minus 2 plus this thing equals 2. It's exactly the same condition that we used here. The sum of these things has to be equal to 3, and here the sum of these things has to be equal to 2. That's because the relationship between this one and this endpoint and this one and this endpoint is exactly the same. We're just going one more than the powers are involved, and so it's the sum of all those things has to be equal to 2, and that means that this number has to be 0, so that 3 plus 1 minus 2 is 2. So what is this polynomial actually? Well, this means that this polynomial is actually the polynomial 3 plus 1 times alpha minus 1 minus 2 times alpha minus 1 squared. And if we wanted to, we could rewrite that in terms of just ordinary powers of alpha, and it turns out to be, in fact, not a cubic. It's a degenerate cubic. It's a quadratic, but that's fair enough. Okay, so we've got that polynomial. Now what we want to do is we want to compute its Taylor coefficient vector at the other endpoint, at 2. Well, what are we going to do? We're going to take the coefficient vector at 1, and we're going to multiply it also by P1. It's exactly the same relation. To go from the coefficient vector at 1 to the coefficient vector at 2, we're going to multiply by the same Pascal matrix P sub 1. And you can check. That's what we get. All right, now the pattern is kind of clear. We're just going to keep on doing this for as many points as we have. So at the next stage, we're going to take this vector here. We're going to copy it again. At least we're going to copy the first 3 entries. And the last entry is going to be determined by the condition that the sum has to equal the value at the next endpoint, which is 2. And indeed, the sum of these things is equal to 2. That's why we chose 5. And the meaning of this is that now this third polynomial in black here is actually 2 minus 3 alpha minus 2 minus 2 alpha minus 2 squared plus 5 alpha minus 2 cubed. We're now talking about powers of alpha minus 2 because it's a Taylor vector at the point 2 that we're talking about. And if we wanted to, we could expand that out, and here's what the polynomial happens to be in powers of alpha. To get the next endpoint Taylor vector, we take this vector, multiply it by the same Pascal matrix P1 to get this one here. Then finally, for the fourth polynomial, P sub 4, we're going to take this Taylor vector, which is the Taylor vector for P3 at that endpoint, copy it over, at least copy the first three terms, adjust the fourth term so that the sum of all these things is equal to, in this case, 1, the value of the next endpoint. So it turns out to be minus 22 because the sum here is 23, so 23 minus 22 is 1. And there's the associated polynomial in terms of powers of alpha minus 3, 2 plus 8 alpha minus 3 plus 13 alpha minus 3 squared minus 22 alpha minus 3 cubed. There's what it looks like in powers of alpha. And in this case, because we don't have to go any further, we don't actually need to figure out what its Taylor coefficient vector at 4 is. But if we did need to know that, we would just take this vector and multiply by P1, and that would give us the Taylor coefficient vector at 4. All right, so you could see that if somebody now came along and said, wait a minute, I've got a few more points that I want to add here. Okay, no problem. We just carry on. At each stage, there's no more choice. The only choice that we had was in the initial configuration when we happened to decide to use these two values, but everything else is then completely determined. And I should say that inevitably what happens, as with all mathematical computations, is the more you compute, the bigger the numbers generally get. So we have to expect that the numbers are going to get big, and we see that they do. And correspondingly, the polynomials that we get, even though they're cubics, they become a little bit wilder, right? They have to go up further and come back down. They get steeper, generally speaking. And so if you have lots of points, that's going to be an issue. Okay, you're going to find you're going to have lots of steep polynomials in practice. So at that point, you might say, well, maybe we can choose these in a more efficient way, but that's a whole another can of worms. Okay, but just be aware that you do expect these the later ones to get more and more steep as you carry on. All right, so we see the power of linear algebra. We also see this idea, very important in calculus, underrated idea of thinking about Taylor coefficient vectors and thinking about the relationship between Taylor coefficient vectors at different points, where our favorite Pascal matrices come to the fore to help us. All right, so some exercises for you. So first of all, make sure you understand why to go from the Taylor coefficient vector of a polynomial at k to the Taylor coefficient vector at k plus 1, we multiply by p sub 1. That's what we did, and I claimed it. So to go from 0 to 1, we saw we had to multiply by p sub 1. Make sure you convince yourself that to go from, say, the vector at 1 to the vector at 2, we also multiply by the same matrix p sub 1. Or to go from 2 to 3, or to go from 5.5 to 6.5, if we have to do that. Then just a repetition of the example. So repeat our example, same points, but start, say, with this polynomial, which also goes through 1 at 0, and at 1 it also goes through the point 3. So you can just do the same computation and see what the cubic spline looks like. And then once you've understood that, you can think about a little bit more general case, because we've only proceeding so far step by step, where the steps are each of the same size, of size 1. So what happens if our points are a little bit more randomly spread out? Say 0, 0, 1, 2, 3, 1, and maybe 7, 4. What would be a cubic spline that passes through that? And to make it a little bit more pinned down, let's require that the derivative at 0 is 0, and that the second derivative at 0 is 0. And what that means effectively in terms of the Taylor coefficient vectors is that the second coefficient, which is essentially the first derivative, is 0, and the third coefficient in that vector is also 0. So only the first and the fourth coefficients are non-zero. Okay, so there's a little bit more to say about this. In particular, there's this question of addressing, well, how do we go from Taylor coefficient vectors from 3 to 7? We haven't really talked about that. We've only gone from 0 to 1 or from 1 to 2. That's an interesting question. We're going to talk about that next time. So we're going to formalize a little bit about our discussion of change of basis that we've informally been talking about here and in previous videos too. And so we're going to have a bit more formal layout of this change of basis framework, which is often a confusing point for many students of linear algebra. And we're going to illustrate things by talking some more about this very interesting application of these Taylor coefficient vectors. Quite a significant application to calculus. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.